Electric cars address a major source of greenhouse gas emissions. Central to these vehicles are powertronic components like traction inverters, which contribute electrical losses, reducing vehicle range. Modern powertronic components utilize wide bandgap devices to reduce these losses thanks to their high switching and transient frequencies. But when these frequencies interact with module parasitics, they create electromagnetic interference issues. I am Sourish Sinha, and my research is focused on developing high-density power module packages that optimizes internal parasitic impedances while incorporating shield layers to mitigate EMI and partial discharge-based electrostatic interference in high-voltage power modules. To address the differential mode EMI, I employed the parallel plate interconnection-based magnetic flux cancellation technique in the high-frequency loop of the half-bridge circuit with integrated gate driver to mitigate both gate loop and power loop inductance. While this approach reduced loop inductances in the double-sided and stacked die power modules, the inductance is not low enough to be implemented in a low EMI converter solution. Thus, I adopted a 3D heterogeneous power packaging technique to create ultra-dense chiplets with 160 dies in 64 mm square area. The design achieves vertical transmission of power delivery and parasitic inductances of few picohenries. The modules were fabricated and tested for high switching speed and insulation breakdown voltage. The results demonstrated that 3D heterogeneous packages can reach tens of megahertz in switching frequencies and substantially low inductances as well. However, differential mode EMI is not the only concern. 3D heterogeneous structures outperform the double-sided and the stacked die power modules even in common mode EMI. But not to discard the double-sided module completely, I addressed its high CM current issue by developing a CM large signal model that tunes the coupling capacitances and challenges the conventional approach of only minimizing the coupling capacitances. Instead, I proposed an intelligent way of distributing the capacitances to reduce the CM current. Additionally, I developed an impedance balancing and selective resonant frequency cancellation based model to further attenuate the CM current by a massive 34% in the double-sided module. Importantly, EMI is not just conducted but also radiated. So I proposed a novel ferromagnetic layer-based shielding technique that attenuates the commutation magnetic field by reducing the magnetic flux density by 76% and also the power loop inductance. Finally, modules also need to minimize the electrostatic interference. So I developed a model that converts the vector electric field analysis to scalar calculations, thereby allowing a massive simplification in determining the optimal layout for achieving the least electric field intensity and hence partial discharge. I hope that my research on high density packaging, CM and magnetic field attenuation using shield techniques and capacitance model for partial discharge inspires new ideas.